Hello everyone, today in Dynamics of the Lithosphere we will go through the third part of the lecture on elasticity and regional isostasy. So in the last lecture we have derived together the master equation for flexure. This is this fourth order differential equation for W. So on that side you have the fourth order derivative of W with regard to X multiplied by D, which is the rigidity parameter here, which includes both the effect of the thickness to the power 3 and effect of material parameter elasticity modulus here, Young's modulus, and Poisson ratio. On the right hand side, you have Q, which will be a force per area, the pressure, unit Pascal, minus P times second order derivative of W with regard to X. P here will be a horizontal force in unit Newton per meter. W is the quantity of interest. That's the deflection. That's what we want to predict with the model. So you see W on this example of a plate bending in the subduction zone, the outer rise here, this is the quantity W that we wish to predict. And here, for the case of a magmatic intrusion that caused the development of a laccolith, we see W will be this displacement here that we wish to predict with our equation. So the deflection W will vary with space, and it is function of forces P, load Q, and rigidity of the plate which is being deformed. The question now is how to calculate those deflections. So the thing is that we have an ordinary differential equation of order 4 here, and in order to solve for W, we will need to integrate this equation. In the first example, which is the topic of today's lecture, we will study the case of the laccolith. In next week lecture, we will apply the same equation. We'll get a solution for the lithospheric flexure. So let's go for the case of the laccolith. So again, we have our master equation, and for the case of the laccolith, we will assume there is no horizontal tectonic force. So we will set P here equal to 0. That simplifies our equation and cancels out the term that contains the second order derivative of W with regard to X. So the equation simplifies to this, and one can isolate the fourth order derivative on the left hand side. It's equal to Q divided by D. Again, here you have the sketch of the model configuration. We have a rigid base here. There is a hole through which the magma is being intruded in the crust, and the plate here is being bent upwards. So again, we want to find W, so we need to integrate this equation 4 times. You know that each time you will integrate this function, you will produce a constant. So here, if we integrate 4 times, we get 4 constants. And to define those constants, we will then need to use boundary conditions. So let's go through the solution procedure, and we now state the different boundary conditions. We will assume that dW dx, so the first order derivative of W with regard to X, is equal to 0 at position X is equal to minus L divided by 2 and at L divided by 2. We will also assume that W will be equal to 0 at each end of the model. Position minus L divided by 2 and plus L divided by 2. So you see that obviously here X is in the middle of the domain. That will be X equals 0 minus L divided by 2 and L divided by 2. L being the entire length of the model, of course. So let's start with integration step number 1. If we integrate this equation once, we will drop the order of the derivative by 1. So here we obtain the third order derivative of W, and we introduce the first constant here. Here Q gets multiplied by X. In the second step of integration, we drop again the order of the derivative here. The preceding constant A gets multiplied by X. The preceding term of first order with regard to X becomes second order, divided by 2. And we produce a new constant B. Let's proceed to the third integration. The third integration, the derivative here is only at the first order. And we already had produced third order term, so x to the power 3 for this term here. You see that the constant which is introduced at the third step called C is present here. And let's do one last step of integration. So this has the effect of obtaining W now, instead of having its derivative. So we have the product dW, but we have produced terms, so x to the power 4 here, 3, 2, 1. And the last constant is D. So we have 4 constants, and we have W here. So one thing we can do is to work with this last equation now, and we can solve for W. So we take this equation, isolate W, and we get this equation with multiple orders of x here, up to the power 4. So the point now is that we have a general solution for W. So W depends on x at different powers. It depends on Q, which will be our load. But it also depends on 4 coefficients, 4 constants, A, B, C, and D. And in our case, we want to also evaluate those constants, and to do so, we will use boundary conditions. So let's recall the model configuration. 0, x equals 0 is in the middle. We have minus L, the total length, divided by 2. This is this coordinate, and we have L divided by 2, which corresponds to this coordinate. We have W, the deflection, which is equal to 0 on each side of the model. So these are 2 boundary conditions, and we have 2 other boundary conditions which state that dW dx is equal to 0 on each side of the model also. So we're going to use the first boundary condition, and you see that this boundary condition, it relates to dW dx. So let's look again at our different integration steps. Remember, we had 4 integration steps. This one has d to the power 3, W dx 3. This is second order, this is first order, and this is order 0. So if we work with dW dx, we definitely want to work with integration step number 3. So we are going to use this equation because the boundary condition is relative to this quantity. So we select integration step number 3 and introduce dw dx equal 0 for the value of x being equal to minus L divided by 2. One obtains this equation. Function of L, A, B, and C. This is the use of boundary condition 1 out of 4. The second step is using dw dx equals 0, but this time at the coordinate x equal plus L divided by 2. And you will obtain this equation, only the sign changes here. So we have a second equation. It's still using integration step number 3. So let's move to boundary condition number 3. So boundary condition number 3, it directly concerns W and not a derivative of W. So to work with this boundary condition, we want to use integration step number 4 because integration step number 4 does include W and not the derivative of W. So now we can set W equals 0 and L equal x equal minus L divided by 2 everywhere. And you obtain this equation. Again, function of A, B, C, and D, because we are at the step number 4. So we obtain a third equation here. And let's move to the use of the last boundary condition, 4 out of 4. And this is now W equals 0 at x equal plus L divided by 2. And we get a fourth equation here. So to summarize, after using all these boundary conditions, we obtained 4 equations with 4 unknowns. The 4 unknowns are A, B, C, and D, the 4 constants that will make our general solution specific to our problem of the laccolith. So for equation 4 unknowns, one needs to solve this linear system of equation, and I now give you the solution. The solution is A equals 0, B equal L to the power 2 times Q divided by 24, C is equal to 0, and D is minus L to the power 4 times Q divided by 384. So using these values now we can finally get an expression for W as a function of X. And now we have the second order and fourth order powers of X, which are here, and now L features into this equation. So that's the specific solution to this model configuration. So we can use this to study the case of the laccolith. One may also go a step further and try to determine the largest deflection. From the model configuration, you understand that the largest deflection will be obtained here in the middle of the domain. That's the maximum one. And the middle of the domain in our case is x is equal to 0. So from this equation, if we evaluate this for x is equal to 0, this term vanishes and this term also vanishes. So that's the expression for the largest magnitude of deflection. So now we can move forward and apply this equation to study the case of a placement of a laccolith. Here I took the example from a paper of Carlino, 2012, where he applies the model of elastic flexure to the emplacement of the mount or the constructions of the Mount Epomeo in Italy. So the Vesuvius is here, the Campi Flegrei, the Bay of Naples. So we are in this location. So that's zoom, this part, and you see the Mount Epomeo is located here, and it basically erupted in the last 50 kiloyears. That's a sketch where you see here a model, the surface model of the Mount Epomeo, and different variations of the model of emplacement of laccolith that we have been using already in this lecture. So you see the different proposed stages for the growth of the laccolith, and here you see also other processes that could happen during the emplacement of the laccolith. For example, a fracturing associated to the bending, and potentially dislocation of the top block to allow for magma to erupt at the surface. So now what you're going to do for the exercise is to apply the equations we derived today to the study of this case. And one part of the exercise, you will have to predict the deflection profile, and you will use the following parameters that will be also defined in the notebook which I provide to you. And another part of the exercise will be that you will have to predict the distribution of horizontal strain and horizontal stress inside the plate. So you will have to construct these diagrams of strain and stress. These will allow you to identify the locations where the plate, which is being bent, is in extension and where it is in compression. And you will also obtain absolute magnitude of the stress inside the deforming plate. So as a conclusion, elastic flexure can be used to predict the displacement, deformation, and stress induced by a magmatic intrusion. So here we saw the case of the laccolith. It is a powerful model, which is very popular, and it allows to predict already a lot of things, but it also has some limitation. The main limitation here is that everything is based on elastic rheology. So the model is very useful up to a certain point where it cannot predict the failure, or it cannot also predict the creep of the material. But at the first order, you will predict deformations and deflections from the elastic model. So that's already a lot of things. In the next week, we take a very similar model, still the flexure model, but we will apply to the deformation of the mantle lithosphere. So thanks for your attention, and good luck with the exercise.